Good evening and welcome to AP Statistics Office Hours. My name is Curtis Brown and I am your host. I'm here with Daren Starnes. Daren, I'm super excited that you are here joining us yet again this fall. And we've got a whole bunch of really cool things lined up for us. Daren, you've put together some really good problems for us. So let's go ahead and get started.
Sounds great. Thanks, Curtis. And I'm looking forward to letting Curtis show off some really nifty features of the TI-Nspire along the way. Let me see if I can share my screen here and just make sure all of the slides are going to work out.
That
Seeing
looks
everything
good.
okay there? All right,
Looks
excellent.
great.
Let me just launch the show. So tonight, our plan is to show how the TI-8384 and the TI-Nspire can be used to support, in particular, teaching and learning in units 3 through 5 of the AP Statistics course and exam description. And in case you haven't memorized what those units are yet, Unit 3 is about collecting data. Unit 4 focuses on probability, random variables, and probability distributions. And as an aside, from my experience, this is one of the most challenging units for students each year. It just has a lot of complex mathematical thinking in it. And then Unit 5 on sampling distributions. One thing to mention here on the CED is that combining normal random variables is part of Unit 5, as are normal random variables themselves. They just had so much content in Unit 4 that they couldn't fit it all. So we're going to focus mostly on the beginning of Unit 5 in this session, but I promise in the next session, we're going to do some really snazzy things with the TI-Nspire. By me, I mean Curtis, to show you how sampling distributions then connect to inference. Once again, as with our first office hours, we're going to take a look at a real world scenario that will connect several concepts within the units, and we'll show you how to answer some pretty challenging questions involving that context. And then we want to hear your questions. Curtis, how would you like folks to send questions to us?
Everything through the chat would be wonderful. Anytime they've got things they want to put in there, they can just put it in the chat. And we'll also be posing a few questions, perhaps, or at least getting people's input. So just know there might be a slight delay in the way that we can answer those questions. But yeah, we'll look at those in the chat.
Sounds great. All right, let's talk about our scenario here. This is based on a real world occurrence. I can get into that in a minute, but many of you know that when you go to a fast food restaurant, you might order some kind of soft drink, and some arrangement is made to get you a cup and then to provide access to a lid for that cup. Now, at some restaurants, they give you both. At some restaurants, you get the cup at the counter and then you go get the lid from a little dispenser. But however you do it, the issue is that you need the lid to fit snugly on the cup. There are a couple of problems that you could run into. One is that the lid could be too small and just not go on at all. And the other is that the lid could be a little bit too large, in which case it may not quite seat on the top of the cup. It's really
I hate
only
that when that happens.
Yeah, it's very annoying if you think it's seated on the top of the cup and it looks like it's seated on the top of the cup, and that's how this problem got inspired. Was one time I was out at a fast food restaurant, and my very gigantic sweet tea had a lid that looked like it was seated on the cup, but alas, when I squeezed the cup, the lid popped off. I tried to show my agility and balance and failed, and the whole large cup of sweet tea went right down the trousers. So
yes.
This has
had that happen.
Personal meaning to me. So here's the scenario. I did a little research online to learn about the sizes of cups and lids. And so here's one restaurant supplier who claims that the diameter of the large lids they're providing follows an approximately normal distribution with mean 3.99 inches and a standard deviation of 0.01 inches. Now the large cups have a diameter that the supplier says follows an approximately normal distribution with a mean of 3.96 inches and a standard deviation of 0.015 of an inch. So let's just assume for now that the supplier is telling us the truth. We don't have any reason to think otherwise. But for a lid to fit on a cup, the way that the products are designed, first of all, the lid diameter has to be larger than the cup diameter. If the lid's smaller than the cup diameter, it's not going to work. So it has to be larger, but not too much larger, or it won't seat around the rim of the cup. So it has to only be larger by up to and including 0.06 of an inch. Whew. So we've got two approximately normal distributions, one for the cups, one for the lids. We have the mean and standard deviation for them, and then we have a goal of trying to get the lid to fit on the cup. So I don't know about you, but Curtis, this already makes my head hurt thinking about two separate distributions.
Yes. I'm going, wait a minute. I gotta think about this mean and this standard deviation, that mean, that standard deviation. How do we combine those two together? I know there's some fancy arithmetic I've got to remember. So yeah, there's a lot going on.
Exactly. So the goal of this first problem is to just find the probability that a randomly selected large lid from this restaurant will fit on a randomly selected large cup. We hope it's a good probability. We hope that the suppliers are providing cups and lids that are going to go together nicely most of the time.
Yeah.
So this is just a summary of the problem again, so we can refer back to all those numbers. And I'm going to go a little different route. I'm a math guy at heart, but one of the things I've learned in teaching statistics all these years is that simulation is a really powerful approach when the math might be complicated or just downright puzzling. So I'm going to suggest we start with a simulation approach, and then we'll come back and take a look at the more mathy approach that some of us are thinking and see how that matches up.
Yeah, I think that's a really good idea. I think, a lot of times we get caught up, or at least I get caught up in trying to do this math formally the first time that my students see it. And it's really beneficial to get an idea of what am I supposed to be expecting to happen, right? I mean, that's what we're trying to do with this simulation, is try to get ourselves thinking about this in a ballpark, especially training ourselves to think about simulation for things that, unlike this one where we can eventually do a nice computation for it, there are things that we can't. And just reminding our students and reminding ourselves that simulation is a key to being able to compute things that we couldn't before.
Exactly. And so with that said, I'm going to break over to the calculator now and think about how I might do a simulation for the diameters of the lids, and also a simulation for the diameters of the cups, and then how to put the two together to figure out whether the lid fits or doesn't fit. All right, so that's a lot to think about, but I'm going to do this on the 8384. Curtis is going to show you some things about the Nspire and how it's similar and different. The first thing I need to do is simulate the lid diameters. So I know that they follow approximately a normal distribution. So if I go to math, probability, and random norm.
Daren, if you're showing your 84, you need to put that up there on the screen. We can't see it.
Thanks, Curtis. I must have done a bad share. Let's try again.
No problem.
I must have just shared the PowerPoint. I hate it when I do that. I hate it when I do that.
Yeah, I've done that a few times myself. It's very easy to do that.
All right, this time I'll confirm that you're seeing my calculator screen.
Yes.
All right.
Good to go.
All right, here we go. We're going to do math, probability, rand norm. So what we're doing is we're simulating observations from a normal distribution at random. And then it's going to prompt us for the mean of that normal distribution. So we want to do the cup lids first. They have a mean of 3.99 and a standard deviation of 0.01 inches. 3.99, 0.01. And now we need to do a lot of trials of our simulation if we want to get a good estimate of the probability. So I was sort of thinking about 500 would be, no, not 5,000. We got to finish this in a reasonable time.
Yes, let's generate just 500.
So I don't want to press enter yet because I want to store those in a list. So I'm going to press the store button and just store those into list one. So I'll remember that list one is the lids diameters. and we'll let it do its thing. And voila, we can see that the diameter of that first simulated lid from the supplier has a diameter of 3.98 inches.
That was a lot faster than picking 500 cups and measuring them.
I love simulation. So we're going to do that one more time for the cups. That was the lids. So we'll do rand norm. And this time for the cups, they follow an approximately normal distribution with a mean of 3.96 inches and a standard deviation of 0.015 inches. And again, we'll simulate 500 cups at random from this approximately normal distribution. And we'll store that into list 2. So while it's thinking about those, producing those, we can start thinking about how we're going to attack the problem. We can see that this first lid is bigger in diameter than the first large cup, and it is larger by an amount that's less than 0.06. So that one's good. The next one, 3.99 versus 3.96, that one's also good because the lid's bigger than the cup diameter, but not by more than 0.06. And so we want to really look at the difference between the lid diameter and the cup diameter. We want it to be positive. So I'm thinking, let's do L1 minus L2 and store that into L3.
Yep.
So you can see now we've computed the difference in the diameters of the lid and the cup, subtracting lid minus cup. And the first two are both winners, both positive and both less than or equal to 0.06. But we sort of want to know how many of those there are in the entire list 3. There's 500 pairs of cups and lids, and we need some way to count how many there are. So I've admitted to Curtis, and I'll admit to all of you, I tried just messing around with list 3 and sorting it, and then like counting how many negatives there were and counting how many numbers there were that were greater than 0.06, and that took forever. So I didn't think that was the best way. And then I remembered from a long time ago that there was this Boolean algebra possibility. And so I'm showing this PowerPoint slide here so you can see what I'm about to do. It occurred to me that I just want L3 to be greater than 0, and I also want L3 to be less than or equal to 0.06. But I want the calculator to tell me if that's true, and it'll return a 1 if it is and a 0 if it's not. And then you can see what I'm going to do next is just add up list 4, where all these 1s and 0s are stored, and find out how many there are.
That's a beautiful thing about that Boolean algebra. You can use the 0s and 1s on the 84 to get you what you're looking for.
Now, the thing I always have trouble remembering how to find is the connectors.
Oh, sure.
So it's under
the
test.
Logic. Mm-hmm.
So I've got L3 greater than 0, and then I need a connector of and.
Yep.
And then I need L3 second math or test less than or equal to 0.06. So I have to admit it took me a little while to remind myself of how that worked. And then we'll store either the 0 or the 1 corresponding to each pair in list 4.
Sure enough.
There they are. And then I just want to find out how many pairs are successful where the lid fits on the cup. So I'll just do second stat math and sum, and I'll add up list 4. So this is the number of pairs that fit out of the 500, and today I got 448.
Okay.
So if we're playing along at home, that's an estimated probability that the lid will fit of 0.896. When I did it in preparation for the session, I got 451 out of 500, which was a little bit more, 0.902. So pretty close, pretty close.
Yeah, real close. Real close.
And in case you wanted to see what the sort of internal screen looked like there's what the internal screen looked like when I did it beforehand. I'm just going to hand off to you and
sure,
let you show the Nspire.
All right, Daren, I think I'm ready. If you hit stop share, I should be good to go. You can see my screen okay?
Looks good.
All right. So I think for the Inspire piece of this, what I'll do is I won't walk you through all of the steps. I've already done all the pieces. Daren kind of did the logic for you. What I just want to show you is maybe some of the differences in the similarities of the way that this can be done or can be looked at. So I computed the lids just like Daren did with list one. I just named my list, which is one of the really nice advantages of being able to do this with Inspire. I can use lists that are named. I can type them in using the keypad on the calculator, or since I'm on the software, I was able to use my keyboard and just type those in. Sometimes you get a little bit long-winded on the keyboard. So as a teacher, if you're developing this stuff, be careful. Your students may not be able to type that many letters, or at least not as fast as you can. Just something to keep in mind. But all the rest of it is pretty much the same. The random normal commands and are the same. So I was able to create two lists, one called lids, one called cups, and then one called difference or diff, which was the lids minus the cups. I created all of those first, and you can check those out here. I just dumped them into the list so you can see that they were complete. If I ever wanted to scroll down for some reason and look at the 456th cup, I could check out the difference between it and its lid. I also at the bottom here, and this is one that I probably will do with you just to show you how it works. I calculated the number that fit. So I defined a variable called fit, and maybe I'll make a new one called num fit, just so you guys can see how this works. Underneath of the control and the template sign, if I use the control and the template sign on a calculator, I'll get this definition. So I can define this variable. I can define it to be a list or something else. But I'm going to use this thing called count if. It's a command that actually searches through. So I'm going to go through a list. So I'm going to call it count if. And what it's going to do is it's going to search through a list of values, and then it's going to look at a condition that I'm going to give, and it'll tell me the number of times that condition is met from that list. And so in my case, I want to look through the list diff, right? And it gives me the bold because that's my variable that I've already predefined. And then the condition that I want to know is the value in diff greater than 0 and less than 0.06? So I'm just going to type that in exactly like you see it up above. The idea being 0, less than, and the less than on the calculator screen is over here underneath of the control, and then equals. I get using the keyboard, Daren, sometimes, and I forget that I need to demonstrate this the other way. So you can also get this question mark, the question mark, which is sort of our dummy variable, our holder variable. We're going to use that underneath of that question mark, an exclamation point button there. So I'm getting that. And then I'll go back here to control and equals and pull up my less than or equal to, and then I'll give it the 0.06. And I should get actually the same answer because I haven't changed my
Let's hope.
I haven't changed my randomness in my other two. So I got 456 as opposed to your 451. So Daren, I'll stop there and let you get back to it.
Sounds good. Just confirming that we're back where I left off.
We are.
Excellent.
We're good to go.
All right. So I know there are some folks out there watching who are thinking, come on now, you need to do it like the right way. Well, I would argue that we've got a very acceptable way that fits within the course and exam description. I'm pretty sure simulation is in there. And I'm also pretty sure that dealing with normal random variables is in there in Unit 4 for the simulation, Unit 5 for the normal random variables. So I think we've done a pretty good job here of achieving the goal of the problem.
I'm curious if anybody out there would have approached it the same way that we just did. I'd like to know if anybody is thinking, oh man, I never thought about doing a problem like that with simulation. I know there's simulation we do for other things, but doing one of these random variable ones to kind of get us started, that's actually a really creative way to do this. I was encouraged to see that.
Well, maybe I can scare the people who were going to do it this other way by just showing the other way. I mean, that the algebra of random variables is what Curtis alluded to earlier, and this is kind of the traditional way for at least varsity level mathletes. I mean, you have to have some math chops to pull this thing off. So let's let L be the diameter of a randomly selected lid and C be the diameter of a randomly selected cup. The variable we're thinking about is L minus C. We need it to be between 0 and not including 0 and up to 0.06, including that value. What do we know about that distribution? Well, thankfully, we're combining two approximately normal random variables, and they're independent. The cup diameters and lid diameters are independent. So that gives us two nice things. One, it tells us that the difference is going to be approximately normal. And two, it helps us figure out the variance and standard deviation of that combination of variables. The mean of the difference is pretty easy. It's just subtracting the two mean diameters up there for 0.03 inches. The variability only works, this Pythagorean theorem, if the random variables are independent. So because they are, we can add the two variances together, the 0.01 squared and the 0.015 squared, and then take the square root to get the standard deviation of 0.018. And we're not even done yet.
Well, all we know is what the mean and standard deviation are. Well,
yeah, we can draw the picture now.
We draw the picture.
Yeah, and there's all that's what we know so far. We still haven't solved the problem. So what I thought we would do is just take a quick look at the graph of this thing so we know what we're dealing with. So let me clear all this off. We'll go into the y equals menu. We'll turn that plot off so I don't make a mistake. And then we'll come back here. So I really want to do second vars and normal PDF. For the x value, I really just want x because I'm going to graph the normal probability density function. We agreed earlier that the mean was 0.03 and that the standard deviation was 0.018. We'll just paste that in. Now the problem I'm going to have is the window. Like the window is not something off the top of my head I would know, but I can figure out the x part of the window pretty well. So let's do that. I showed a little bit of this trick in the first session in terms of figuring out the window. So for the minimum, I want to start at 0.03 and I want to go down at least 3 standard deviations, which is the 0.018. You could do 4, but I'm just gonna do 3. I like to go out at least 3 standard deviations from the mean of the normal distribution. Sure. And then for the other one, we've got 0.03 plus 3 times 0.018. And you can see I'm letting the calculator do all the work. I don't want to have to mess this up right here live on YouTube for forever. So I'll use the scale of 0.018. Now I have not a clue without cheating what the y minimum and maximum are supposed to be, but you know, I could do something like zoom fit and kind of cheat because I know what the x window is, but I don't know the y window. But now I'm going to go look at what the calculator picked and I'm going to say, yeah, I wouldn't have picked those numbers, like 0.24 to 22.16. So maybe I might do something like a little bit below the horizontal axis to, I'm not sure if I need to go too much higher, but I could go to like 24 and I could just go up by 2s.
I was really hoping you'd choose 25 because.
Yeah. You like 25? Is that what you've got?
That's what I've got.
Darn it. Well, whatever Curtis does is even better.
No.
So I'm going to hit trace just to convince you that really is the normal probability density function. So I want to show the area we're looking for on this picture, and having the normal PDF here makes this a much easier process. So I'd like to shade the normal curve that I've just drawn in between 0 and 0.06. So if I go to the distribution menu and draw, I can do shade norm from 0 to 0.06. My mean was 0.03 and my standard deviation was 0.018. Blue, sounds good. Let's just shade that in and voila, there's the answer, but that's not fair using that. Like we have to work this out algebraically. That's what you wanted, right?
Right.
All of you wanted that out there. Well, there's the answer again. I'm wondering if in the 21st century that might not be good enough, but maybe there'll be a question somewhere on an assessment where students have to work out some of the algebra details,
For
heaven
sure.
forbid. So these are just documenting the window information again. But that's
For
not
sure.
really how you do it. Like stats teachers know, we do this and we love it because it's just so beautiful to
Right.
convert to a z-score, both endpoints. The z-scores happen to be negative 1.67 and 1.67. We look it up on our table, I presume, from the 1900s, and then we get 0.9050 from the table, which isn't even as accurate as what the calculator gave us with 0.9044.
Right. Right. So there's
And
definitely an advantage from using the calculator there. Yeah.
that's because we rounded the z-scores. I mean,
Yeah.
we could
Yeah.
have gotten a little better, but
Sure.
we wanted to use table A because that's what we like to do.
Right. We get comfortable doing that.
So that's the alternative to the simulation, and I would argue that some percentage of students will have a really, really difficult time executing method 2 properly.
I would agree with that argument. I did see in the comment section some folks agreeing with us that the idea of starting this section of the course certainly with simulation is really advantageous to students and really good. I am going to put out one note of caution, Daren, and that is that you snuck one by us all by doing the normal PDF drawing first. When you went back and used the distributions menu and did the shade normal distribution, your window was already set up, ready to go. That was very shrewd of you and a good strategy to make sure that showed up very nicely. That if you did not do that beforehand, you would not have gotten such a nice, beautiful picture because that shade normal does not auto scale the picture. So you have to set up that window to begin with, which actually, Daren, I really liked the way that you did that. That's a very logical and a good way for students to think about how do I come up with the boundaries that I actually am interested in to do this, and then take advantage of the Zoom Fit to be able to come up with what's a reasonable Y scale.
Well, I appreciate that. To be fair, I learned my lesson from session 1 when I airballed the shade norm and realized I hadn't set the window yet, and it just shaded nothing. It was just a big blank screen. So this is how you do it right. I'll learn from your previous time.
Right. So that was really good. That was fantastic. Well, I've got just a quick view on the Nspire. If you want to give me the ability here to
You're good.
share that. So are we good to go? You can see the screen here. So Nspire, same thing. I set up the window in the same manner that Daren did earlier by choosing to do plus and minus 3 standard deviations on either side. The key difference here is that on Nspire, when I do the normal CDF calculation and I choose that from the menu, I can get it from probability or statistics. Seems to make sense for me to grab this from the probability distributions menu. So I can grab that normal CDF computation here and do that computation. I don't have the option to shade this normal when I grab that. So when I pick this up off of I'm going to have to go back to probability and distributions and grab that normal distribution. I can go ahead and type in the values just like Daren did before, which were what, 0.06. The mean is
0.03.
0.03 and the standard deviation is 0.018, right?
Yep.
Okay. But I don't have an option here to draw. And so when I'm on this page, I do have to actually make a connection between what I'm doing with a probability density function and what I'm actually computing whenever I do this normal CDF, that accumulation under a curve. And so for your calculus students, this is a really nice reminder that when I'm looking at a curve and I need to accumulate area under a curve, that's what we're doing in these problems. So I actually needed to do an integral to compute that area here. and I'll delete that and go through that process just to show you guys that what I want to do here is I want to analyze, I want to analyze the graph, and I want to do an integral. And I could, try to select it by using my arrows, but I can also just type in the fact that I want 0 to be my lower bound and my upper bound to be 0.06. And I can plop those in there and I get my really nice probability there. So I'll pass it back to you, Daren, and let you get started.
Sounds good. So we've gotten through the really gnarly part of our problem. From here, we're going to think about the supplier's claim, and we're going to think about quality control. Because if you think about the types of answers we were getting on the previous slides, we were somewhere around 0.9, whether we did the simulation approach or the calculation approach, around 0.9. So about a 90% probability of the lid fitting on the cup. That's what the claim would lead to. So the restaurant manager is maybe getting some feedback from customers about lids fitting or not fitting, and mostly not. If the lid's not fitting, that's when they're going to get the complaints. So the lids and the cups each come in boxes of 500 from the supplier. That's how they're packaged. And the manager is considering 2 different quality control plans. Here's the first one. The manager will select a random sample of 40 large cups and a separate random sample of 40 large lids, pair them up in the order in which each were selected, and count how many lids fit on their cups. So first part of this is just to think about random sampling for a second. We want to describe how the manager can use a random number generator like the one on the 8384 or the Nspire to take a random sample of 40 cups or then lids from a box with 500 cups or lids. So I'll show the 8384 version. We need to head on into math and probability again to find some kind of way to pick a number between 1 and 500 and to do 40 of them. So I see 2 options that might be appealing here. I got rand_int and I got rand_int no rep. So let's think about this. Do we want the possibility that the same cup might be selected twice? I don't think so. Rand_int might do that. Rand_int just picks numbers between A and B, potentially with repetition. I don't want any repetition. I want 40 different cups. And then out of the lid packages, I want 40 different lids. So I'm going to do rand_int no rep from 1 to 500. I'll pick 40 of them. And then again, I've got it on the home screen, but it might be nice to store that into a list like list 5 so that I can go find those cup numbers pretty quickly. And just documenting my approach. I did it on the home screen there just so we'd have a screenshot. Curtis, have you got the similar one for Nspire? Hello, Curtis.
Muted myself a moment ago. Did you? Did I hit share? There we go. Now I've got it. You should be good to go now. Yep. So I can generate the same thing that Daren, you did this. I filled a list called cups. I've been reusing that variable name, but I'm inserting new problems each time. So I have basically a fresh set, so I can redo this over and over, called cups, using that same sequence command that you saw on the 84 1 to 500. And the default is by ones. And so here's my list of cups. Now, the difference here, Daren was able to select his cups by doing a random integer no repeat. Here's another place where the TI-84 actually has a feature that the Nspire does not. There is not a random integer no repeat on the Nspire. However, there's a really nice command that gives me the ability, which I think is really a little more pedagogically sound, or maybe something that a student can understand a little bit closer. Because what we're really going to do now is I've got this sample. I've named a variable called sample. And that sample is actually going to be a random sample from this list of cups. So I've got a list of 500 cups here. I won't scroll through all of them, but you can see that my numbers go off up to the 500. And here I've collected a random sample from that value cups, and I'm going to grab 40 of them. And then this little one gives me the ability to either collect with replacement or without. If I select it with a 1, that gives me no replacement. So I'm going to select and then set that cup off to the side. If I put a 0 there, that tells me that I'm going to go ahead and select that cup, record it, and then dump it back in the bin and draw a second time. And so I can recalculate that. As a matter of fact, I can use Control R and recalculate this a whole bunch of different times. And you can see that each time I'm selecting a new set of 40 cups. Really kind of a powerful piece for students to understand that idea of random selection from a different list. So Daren, I'm going to stop share. And,
Perfect.
Give that back to you.
We're going to use that feature that Curtis showed, I predict, in our next session. I'm in my mind already picturing it coming in very, very
The crystal
handy.
ball it's starting to get a little bit clearer, huh?
I can see it. So we've talked about how to randomly select our cups. All right, well now, having done that, how many lids should the manager expect to fit if we assume the supplier's claim is true, which is what we've been doing all along, because that would be an indicator of whether the claim is believable or not. So we're going to let F be the number of lids that fit on their cups, F for fit. And my claim is that F is a binomial random variable with N equals 40 trials, each lid cup pair, and a probability of success on each trial that the lid fits the cup of 0.9044. If you want to check through in your mind that it really is binomial, we've got like a success would be that the lid fits, whereas a failure would be that it doesn't. And then each trial is independent of another trial because we've got a new lid and a new cup from the box. And then we've got our number of trials fixed in advance, and we've got a constant probability of success 0.9044. So just a quick check, it really is binomial. Oh, and there's the distribution, and now it's gone. So on the calculator, we can actually generate this binomial distribution for our random sample of 40 cups with a P of 0.9044. A couple different ways we could do it. I like to use list functionality, so I'll do second stat to get to the list menu, and then do a sequence like Curtis was showing earlier, with my variable being the same as my expression, not arrow X. And I'll start at 0. That's the least value that F can take. I'll go up to 40. That's the largest value it can take, and I'll go by ones. And then I'm going to store that into list 1 because we're all done with that previous list 1. And then in list 2, I want the probability that's associated with each of those potential values. But in the interest of time, rather than like do the binomial probability formula, I'd rather just use the calculator's built-in binomial probability feature. So under the distribution menu, way on down, we've got the binom PDF. The number of trials is fixed on 40. Our probability of success is 0.9044. And our X value is going to come from the values in list 1. Starting from 0, going down to 40. We'll paste that in. We'll store it into list 2. And now we have a pair of lists that I can show you that have the values of the variable 0 through 40 and the probabilities. Just make sure it stops at 40. Yep, looks good. And then I might want to make the graph of that probability distribution. So I can go to my stat plot menu, turn back on plot 1 that was all set up and ready to go. L1 and L2. The problem is we can't use a zoom stat here because we're using a frequency or relative frequency list. So we're going to have to take charge of the window again. And I was sort of thinking, well, like -1 to be a little less than the little to the left of the vertical axis, and maybe go up to 41, something like that, go by ones. And then for the Y, because this is not a function, I'm not going to use zoom fit. this is a statistical graph. So I want to think like maybe negative 0.02 to 0.1 by 0.01, something like that. Not quite high enough. So instead of 0.1, we'll do 0.2. That should get us up there. Nope, not quite enough. 0.3. We're there. Probably 0.25 is 25 must be the perfect answer to everything.
I thought it was 42, but
okay. That's another thing.
That's another thing.
So here's our probability histogram, and you can see the mode of this probability distribution happens to be 37, which I thought was kind of interesting. That's not the expected number, though. Remember, the question was, what's the expected number of lids the manager would find that would fit out of 40? Well, we can certainly use the calculator to find that out. The expected value of any discrete random variable is the sum of its values times its probabilities. So we can do second stat math and then sum of L1 times L2. So that's the sum of the values times their weights, and we get 36.176 is the average number of cups that would fit in random samples of 40 of those. Oh, and then I must have done the variance as well. That's not quite as pleasant. So second stat math, the variance is to do with the sum of the squared deviations around the mean. So we've got to do like L1 minus that 36.176 number, could have used answer, squared times the corresponding weights or probabilities in list 2. This is going to be the variance, so it's in squared units. So I'm going to need to take the square root of that guy to get the standard deviation, 1.86 roughly.
Okay.
Somewhere around there, 1.86. Cut it off on the screen there, so I thought it was good for us to have it.
Yeah,
and then
sure.
For those of you that again are thinking, yeah, that's just like using technology. Yeah, true. It works. It also reinforces the definitions of the mean and the variance. And here it is in the formula version for the binomial random variable. We know it's n times p, and for the standard deviation, the square root of n times p times quantity 1 minus p, and you can see we get the same values up to rounding.
Yeah. Well, I've got kind of a similar experience to share on Inspire, Daren. So yeah, so I did it pretty much exactly the same way you did, Daren, and in that I took again a variable I called numFit, so the number of cup lids that fit against the probability that they fit. I used the sequence generator exactly the same way that you did with x comma x, so my expression and my variable being the same, and then 0 to 40. I'm not including the by ones because that's a default, but of course I could put the comma 1 there if I wanted to. And that generates my sequences. And then right behind it, I did the exact same thing. So the probability of that number of cups fitting is what I called prob fit. And then I used the binomial PDF computation, the exact same one that Daren does there. I typed it in with 40.9044, and then I used that numFit, which was my variable here. So I do really like that advantage of being able to see things named the way that they are, or I can choose the name to be able to name my variable what it is in the problem. So that was a nice feature there. Now, in generating the pictures, which is kind of one of the fun things. So in the data and statistics page, so I inserted a data and statistics page here on my graph here. I'm going to put in that same distribution that we're interested in, which is the number of cups that we had a fit for. So there's my 40 different possibilities, 41 different possibilities that I could have had there. And then what I did here originally was when Daren and I were talking about this a little bit earlier. Since I computed those probabilities in one called ProbFit, I just dropped that in and made a nice little scatter plot here on accident. I wasn't even really thinking about that earlier, so now I have that idea of the ProbFit here showing as a scatter plot. However, in Nspire, which is really kind of a nice piece here, I can actually add in or force that. I'm going to actually force in a Y summary list. I can add a Y summary list and do prob fit here and get a histogram version of this same picture. So I can look at that from a couple of different ways and see that motion happen, or we can plop this in as a distribution that way. And then the calculations work exactly the same way that they did on the 84. No differences here except that I was able to use those named lists. So I'm going to stop share again.
That's great. So many nice things that you can do with being able to name the variables. I'm jealous. All I got's L1 and L2 and its cousins.
You know, you can name those lists, but
I know it's not the same though. It's so much easier. And making that probability histogram, come on, that was easy.
Yes, that was.
You don't have to worry about window management and guessing, and right. It does it for you.
Yes, that was. There's some nice automation there.
So you may have forgotten the manager is trying to test the quality control, and so when the manager took the random sample of 40 cups, in fact, 32 of them fit. For those of you working that out, that's only 80%. Based on the calculations from what the supplier claimed, like it should be around 90, a little bit more than 90%. So the manager's wondering, can I believe the supplier's claim right now? You know, assuming the claim is true, what is the probability that 32 or fewer lids would fit when I do this sampling process? And just in the interest of time, I'm going to go ahead and work through the problem here so we don't miss out on the punchline. And then the second part is going to be like, based on that answer to A, does the manager have convincing evidence that the supplier's claim is false? Because that's a pretty big deal. So I used the binom CDF command. I saw it on Curtis's screen before I took back over. And I found the probability of getting 32 or fewer lids that fit. And I got 0.033. There's only about a little bit more than 3% chance of that happening if the supplier's claim is true.
I'm questioning your supplier.
Yeah. So I think at this point, we have some convincing evidence that the supplier's claim is false. Fewer cups are fitting than should be based on the information the supplier is giving us. So that's not good. Now, our manager had a second quality control plan in mind that I just wanted to share with you. And that is, rather than taking 40 lids and 40 cups, the manager decided that he would just take one at a time out of the cup box and the lid box and see if it fit. And keep doing that, cup, lid, until there was a pair where the lid didn't fit, and just see how long it took. This was a brainstorm late at night, maybe, as they were closing up the restaurant, because that other idea seemed pretty good to me. This one, if the supplier's claim is true, and we use this plan, how many cup lid pairs would we expect to have to randomly select before we get one? Well, up to and including the one that doesn't fit,
Sure.
So again, we can define a variable. Here, W is the number of cup lid pairs the manager has to take to get one where the lid doesn't fit. So I'm setting up a geometric random variable. We're waiting until we get a success, which is where the lid does not fit the cup.
Sure.
Success is whatever we're looking for here in life.
That's right. That's one of those biggest struggles for students, right? Is trying to get the idea of we're looking for a failure.
That's what we're doing. And the probability would be 0.0956 if the supplier is telling the truth, of which obviously, had we used quality control plan 1, we had our doubts about. This is what the geometric probability distribution looks like. I produced it and Curtis produced it in a similar way. And you can see we've got a heavily right skewed distribution this time, very different shape than the binomial distribution from earlier. Here's sort of some information on the expected number of trials it would take to get one that doesn't fit, and how much variability there would be. So the mean and standard deviation of the geometric. And the only reason I include that is because that's kind of a new emphasis in the CED. We really didn't focus on the mean and the standard deviation of the geometric in a formal way in the old course description, but it's in there now. And the formulas are on the formula sheet. And so we can verify what we see on the calculator. It's expected to take about 10.5 on average. And then the standard deviation is quite large. So it could vary a lot from that 10.5 when you do one quality control trial. So of course the manager went ahead and did it. It was late at night, and the manager, I guess, had nothing else to do, and found that it was the 29th couplet pair. Took 29 couplet 29 until the lid didn't fit. Same set of questions, and then I've got the finale question. So assuming the supplier's claim is true, what's the probability it would take you 29 or more couplet pairs to find the first one for which the lid does not fit? And then B, is there convincing evidence that the supplier's claim is false based on this information? So I decided I'd do a geometric CDF. There's my success probability, 0.0956. I want the probability of 29 or more, but the calculator is going to give me 28 or fewer. So this is going to be the complement of that.
Okay.
So I'm getting 0.06, about 0.06. So that's not quite as compelling. You know, a lot of us are 0.05 sort of people when we say something's really surprising or strong evidence. So I don't really think there's convincing evidence that the supplier's claim is false based on it taking 29 couplet pairs. Almost.
Sure.
Like maybe if it had taken 30.
If it would have taken 30, we might have been out of the. So that's one of the really nice, interesting things about having this discussion, right? Is at this point in the course, anyway, we haven't really introduced what this idea of significance yet, and so students really are getting to kind of make a gut check, right? They're thinking about what is that? Okay, so was that 0.06? What that's okay? Maybe one in 16, something
17,
like that.
16,
1 in 16, 17. Sorry, I'm having to do that arithmetic in my head.
Yeah.
But they're kind of getting that, okay, so would I be shocked by that? Like, is that something I would be shocked by? And they really kind of get to think a little bit about that.
That's an excellent point. And I'm going to do a quick recap just to be honest now with everybody that's tuning in. Quality control plan 2 was a little bit contrived. I really wanted to get the geometric in here, so we had normal, binomial, and geometric. And I just want you to think about it for a second. Quality control plan 1 is totally legit. Like, that's a legit strategy to figure out if the supplier's claim is bogus. And it seemed like, based on what happened, the manager found pretty strong evidence that things weren't fitting as well as they should. But with quality control plan 2, think about what it means if it takes more cups and lids, like more searching to find one that doesn't fit. Like if it takes you more and more, like if it took you 40 or 50, the more it takes you, the better they fit. That means they're fitting really well and you're just not finding one where it doesn't. So if the supplier's claim is false, it's actually false in your favor. Like they're fitting too well.
Yeah.
Let it go, people. Let it go. So I would argue that quality control plan 1 is really the one I wanted to show you. And quality control plan 2 is totally contrived and not a good idea unless you want to know if they're fitting a little too well and you need to complain and get a worse supplier.
Right.
So that was my revelation when I was trying to push the geometric random variable in there. I was like, this is totally silly, but maybe not, because you could ask students to kind of process that plan and say, that's a terrible, like, why are you doing that? You want to know if it's fitting too well? Who cares? But maybe in other applications, fitting too well would be a problem.
Yeah, or at least finding something, finding one. I don't know. I'm trying to think on my feet here, trying to think about when I might be concerned that I got too many in a row.
It's just going a little too well for you.
This is just going. I'm starting to be suspicious here. This is a little difficult. So yes, we definitely will be posting the slides of this session here. that we would be very happy to have you guys go and check that out at the bulletin board post on our education.ti.com bulletin board. We will be also posting there the schedule. We'll be updating that bulletin board here in the coming weeks. We'll be posting the schedule of our upcoming sessions in the spring. We'll have 2 more of these office hours sessions planned in the spring. One to cover what are the next 2? What are we doing? What are the breakdown?
So next time is going to be all about categorical data, inference for categorical data. So we're going to show off the TI-Nspire's ability to random sample and also randomly assign. We're going to show you a randomized experiment to compare 2 groups, but it's going to be all categorical data, and we'll finish up with chi-square. And then the final session will be kind of the same thing for quantitative data. We'll look at 1 sample, 2 sample, and then inference about slope. So categorical data theme next time with inference, and then quantitative data theme for the final one with inference.
Well, I'm really looking forward to those 2 sessions coming up in the spring. Again, like I said, we'll have the dates of those up on that bulletin board post coming up in the next couple of weeks. We'll make sure that those are planned out. Anyway, if you guys have any questions, please enter them in the chat or make comments here. We'll be looking for those things, and we'll look forward to seeing you guys coming back in the spring. Thanks, Daren.
Thank you.